All right. Let's talk centripetal force. What color shall we use? How's about brown? It's nice. Looks like chocolate pudding. Okay, so let's look at these two words, okay? Center and seeking. It's your free Greek or Latin lesson of the day. Okay, so a center-seeking force. So what do you mean by that? Well, let's think of Newton's first law, okay? The first law states that it's the law of inertia, right? It just states that objects either stay in motion or at rest unless acted upon by a force. Unless, and you know the rest. Okay, so here's a question. Let's say I have a mass, and that mass is zipping along, right? It's traveling in a straight line. Well, the tendency of this object, due to the fact that it is a mass, is just to continue going in this path, all right? But what if instead of traveling in a straight line like this, I want to make this object follow this path? What am I going to have to do? How do I make this object, which is normally intending or has the normal tendency to go straight, how do I make it turn around this circle? What can I do? Sure, I could put a string to it. String should be straight. Okay, if I put a string on this object, right, it will no longer follow its straight path, right? It will be, if you want, pulled essentially down in this direction. So if I want it to follow this line, I just need to make a force that faces towards the middle. And like, no matter where this object goes, that force still has to point towards the middle at any given instant in time, right? So if the mass comes down here, at this instant in time later on, that force is pointing in this direction, right? So in order to make something go around a circle, we basically have to apply a force aiming towards the center of the circle, right? That could be a rope attached to it. If this is a car, it could be the friction between the tires and the road. We could push it in some way, like we could set up like a wall, like a curved wall to make it follow that curved wall. But at all points along the circle, in order to continue it along the circular path, we need to have a force pointing towards the center at all times. No matter when I look at this object, that force needs to aim towards center. And this is where the term centripetal comes from. So it's a center-seeking force. Center-seeking force is required. Hard to spell. Is required to make a mass travel in a circular path. Now, a centripetal force is a generic term for any kind of force that's making an object go in a circle. Okay, it on its own is not a specific type of force because we could use tension in a rope, like we said. We could use friction to make it go in a circle. We could use a normal force. We could use electromagnetism, and we could even use gravity. Right? You can then scale this up and imagine at the center we have a star with a lot of mass. And around out here, we have other masses that are not quite as massive, but still have mass. And there is an attractive force between them, okay, that we call gravity. So gravity can also cause a centripetal force. We could say that this is the positive center of an atom, an atomic nucleus, right? A positive atomic nucleus will attract negative electrons in a circular path. Now, it's a little bit sketchy as to whether or not this actually happens like this, but it is one way of thinking about an atom, okay? Maybe not the exact right way, but it is one way to think about an atom, okay? So just before we continue, I want to clear up this concept of centrifugal force that you often hear about, okay? So here's an example. Let's say you're in a car, right? You're looking out the windshield, and this is the dash. And let's say you put like a couple of coins on the dash, right? So we're looking out the windshield here, right? Out ahead of us is the road, you know, out there somewhere. And let's say the car turns left. Well, we're strapped into the car, right? We're strapped into the car. And if the person cranks the steering wheel here, right? So the steering wheel looks like, not really, cranks it to the left, we might observe that the coin goes like this, right? So from our perspective, we might say, oh, the centrifugal force is pushing the coin out, all right? This is not the correct way to think about this, right? How we have to think about this is, if we're looking top down on this situation, right? Here's our car. Here's the headlights of the car, right? The car's following the road, and the road turns, right? If we think about the coin, right? That coin has mass, right? It's got mass, it's got inertia. The tendency of the coin is to travel in a straight line, isn't it? If the car turns, okay, it's friction between the tires and the road that are allowing the car to turn, but there's very little friction between the coin and the dash. So essentially what happens is, you as the observer, here's the top of your head looking forward, you observe a coin to move to the right, when in reality all the coin's doing is traveling on its normal path, and the car is turning out from underneath the coin, okay? And you're observing the coin move to the right in relation to the car, but really the coin's not moving, you are, all right? So we'd call this something like a centrifugal effect. And just for full disclosure, let's say the coin comes to rest against the pillar over here, and then it too starts to turn, okay? The centripetal force of the pillar is turning the coin, right? The centripetal force of the pillar is turning the coin. The reactive force pushing back on the wall is a case of actual centrifugal force, okay? Where the coin itself is the reactionary force to that centripetal force. So I don't want to confuse you, but to call anything up here, right, centrifugal force is not correct, okay? We can call this a centrifugal effect, the apparent outward movement of something like a coin, call that a centrifugal effect, but it's not a force. It's in fact a lack of force that's allowing this to happen. If you stuck this penny to the dash with tape, you would not observe it to move outward, right? And that outward motion you feel, right, if the car suddenly jerks and you slam your head here, well, it's because your head tends to, just like the coin, go straight, and the car is coming towards you to meet you. So it's all about a frame of reference and how you essentially perceive yourself related to the vehicle. Okay, so we need to derive some equations to deal with this. So the first thing to note here, right, is that we have an object and it might have a constant velocity. The velocity might be set, at least in terms of the magnitude of the velocity, right? So we might say this is moving at, say, like 10 meters per second. However, there's two parts to a vector, right? There's a magnitude and a direction. The direction of this object is in constant flux. It's constantly changing. So therefore, we say that an object undergoing centripetal motion or circular motion must be constantly accelerating. It's constantly accelerating, not because the magnitude is changing, right? But because the direction is changing. And if you think about it, you do have a force, right? You have a force consistently applied. We know that Newton's law says force equals mass times acceleration. So we must have an acceleration if we're applying a constant force to an object, constant net force to an object, right? But the thing is that that force is always at 90 degrees to the magnitude of the velocity. So it doesn't affect the magnitude, only the direction. Something to think about. So we need to get to a place where we can actually do some math here with this stuff. So let's start with a circle. Okay, let's imagine an object moving around a circle. Okay, we'll have an object there. Actually, hang on. we'll have an object here. And at some time later, the object has moved to here. Okay, so it's moved from here to here. So we'll call this time A, and we'll call this time B. Okay, and then we'll put in a few points. Okay, so these are radii. All right, so this is a radius. This is a radius. Okay, and the object is moving in this direction around here, right? We can say then, you know, centripetal force aims like that and like that. We could say that this right here is chord AB. Okay, so that's chord AB. Okay, are you with me? Okay, we can also say then that we can generate an angle here, and we'll call that angle theta. So now let's look at the velocities at these different times. So at this point in time, the velocity is actually this vector right here. Okay, it's pointing straight. If you think about it, imagine if at this exact moment this object's spinning around and around, at the exact moment this object comes to here, you snip this. Well, this mass would continue on in this direction, right, and travel off at a straight line tangent to the circle. And same here, if you cut it here, it would zip off and travel off tangent to the circle. Okay, so that's kind of an important feature to realize, all right? So when we're drawing the velocity, we want to put it in place here. I think I drew this a little bit too large. I'm going to make it a bit smaller. It just looks funny. That's better. Okay. And we'll put another velocity vector over here, tangent to the circle. Okay, so tangent to the circle at that point in time. So whoops, we'll call this V1, velocity at time 1. Okay, we'll call this V2, velocity at time 2. All right. Now the other thing I think we should probably do is we should just extend this way. Oops, I want to do that with a straight line. I want it to be a line, not an arrow. Sorry, it takes a second sometimes. There, I want that. Okay, so I've simply extended that line out. Okay. Now I want to also say to you, okay, that this is going to be a 90-degree angle, isn't it? Okay, and this is going to be a 90-degree angle, right? Does that make sense? So this here is a 90, and this here is a 90. You with me? Okay, so I just quickly added a few guidelines here to help us prove something about this relationship. Okay, so if you look, this makes a right angle triangle with theta here and alpha here, right, and a 90-degree there. Okay, and then if I look, we have a smaller triangle inside here, which has a 90-degree here. Okay, much like the 90-degree over here, shares alpha, and therefore the other angle has to be theta. Okay, so that's going to be important. So I'm just going to get rid of the guidelines now that we agree that that's theta. Sometimes I just have to prove things to myself to make sure. I feel like I'm lying to you. There might be other ways to prove that as being true. But if we just take this now and we clone these and we lay them out, I want to show you something. So there's a V2, put it there. And there's a V1 there. Okay. And we should also have that theta value here. Okay, so that's V2 and that's V1. So now what I want to do is I want to know if there's an acceleration here, I want to know what is delta V. So remember delta V is equal to V2 minus V1, right? So I want V2 minus V1. So with vectors, to do V2 minus V1, we essentially are going to have to add the opposite vector together, right? So what does that look like? So if we take this guy, copy him, there's V2. We're going to add the opposite to V1. So we're just going to take V1. We're going to like flip it over like that. And then our value for delta V is going to be this. Nope, don't do that. The value for delta V is going to be this. I want that to be an arrow. Please be an arrow. You can be a green arrow. There we go. Great. Okay. So this is now my value for delta V. Okay. So this was V2 and this is V1, right? And this is V2 plus the inverse of V1. So there it is, delta V. Okay, so delta V happens over a time span, right? It happens over a time span. So this is showing our change in velocity for a given amount of time. In other words, what it's showing us is the acceleration of this object, right? Because these happen at, as time passes. And if you'll notice, if I take this and I move it up onto the circle and put it at halfway between here, right? The average between these two values, it will point directly at the center, okay? Which makes sense, right? The acceleration of the object, since the force of the object is aimed towards the center, okay, the acceleration should aim towards the center as well. And the other thing that we also have, if we remember, is we have similar triangles from this whole thing. So I'm going to reorient this thing and we're going to deal with it a little bit. Maybe it makes sense to call this negative V1 actually. That's negative V1. It's not actually V1, it's negative V1. So this angle will still be theta, right? So what we want to do is we want to flip it and we want to see that you can get similar triangles between this and this, okay? This might be able to group it and flip it. Let me see. I want to do this with it. And I want to move it over here. There we go. Not too bad. Okay. Alrighty then. So let's think, oh my goodness. Let's think back to chord AB, okay? And let's do a little bit of calculus, not calculus here. Let's imagine that we have line AB, okay? Line AB, which looks like, just make a line. Let me do it raw. Line AB here, okay. So if you look, I'm going to get rid of some of this junk around here just to make it a little clearer. Don't panic. It's not that bad. Okay. I don't really need these guys anymore. Let's just pop them off here. It's worth the time investment. I feel like it's worth the time investment. So if I look here, okay, I've got chord AB, I've got line AB. A, D, right? And think about what happens as I shrink chord AB. As I shrink chord AB, it approaches being the exact same length as line AB. So the smaller I make this angle, the closer chord AB, which is around the arc, comes to being equal in length to line AB. So at a small enough angle here, chord AB essentially equals line AB, right? As we get smaller and smaller and smaller, these values become closer and closer together. Okay, so basically what we're saying here, right, is that as this angle shrinks, and we mimic that with this similar triangle, right, as we decrease the amount of time, if you want, that this occurs over, right, we come to here, we come to there, we come to there, we come to there, and eventually you get a time so small that chord AB and line AB are the same thing, all right? And what that also means then is that delta v can then be thought about in terms of a similar triangle with this, as long as the time is small enough. All right, so let's make an equivalency here. On this line right here, the v's are like the r's, right? The v's are like the r's, and line AB is like chord slash line AB, right? We don't have a chord here, we have a line. So that's why we have to talk about a very small angle so that you can have a similar triangle from here. So from that, we could say this. We could say that the ratio of delta V to an R should be similar to the ratio of chord AB to a radius. Chord AB to a radius. My mistake. Not that. It should be V. So delta V is to V, say, as chord AB is to R. But we're actually going to say it happens at a very small time period, so we'll change it to this. Delta V over V is equal to AB over R. So we'll change it to a line, because we're saying if this is small enough, then these should be equal to each other. I'm making a mistake in my terminology too, actually. What I should be saying is arc AB and chord AB. It's calling this chord AB. Okay, just fix that. This is arc AB. Arc AB is equal to chord AB. All right, sorry about that. Hopefully you understood what I meant. All right, arc AB approaches chord AB as we shrink. Okay, so delta V here, okay, chord AB there. All right. So now, if we're looking at the arc here, we could say that in terms of our actual literal rotating object, that this arc, right, is actually the distance that the object travels, right? Distance the object travels, which is equal to the magnitude of its velocity times the time it takes to go from there to there, right? So the distance here that it travels is equal to v times t. And if we talk about a small enough one, then we could say that that's actually the same as the chord. So where we see chord, we should be able to say v delta t. So let's come down here and we'll say delta v over v should be equal to the distance here, right, which is v times delta t, right, however long that time is, divided by r. So again, just to reiterate, right, because we're not talking about the arc anymore because it's small enough that we can essentially make it equal to the line, right, and that arc was equal to velocity times time, which is distance. Okay, we can replace chord AB with the velocity, the magnitude of velocity times the time we're talking about, which in this case is a really small amount of time. But that's okay. It doesn't matter how small the amount of time is. So we're going to do a little algebra with this. First thing is we're going to divide off time. So if we divide this side by time, we should end up with this. Okay. And then we're going to multiply both sides by v. Okay, so multiply by v, that cancels a v there. And we multiply by v over on the top. We now get this. And recall from the past that acceleration is defined as delta v over delta t. So what we've done here is we've found a formula talking about the acceleration of an object around a circle. And this is what it looks like. AC, centripetal acceleration, is the magnitude of velocity times the radius of the circle. Okay? So what that means is, let's see here. What that means is, let's say we have two objects traveling around circles. Let's say the velocity is the same in both cases. Well, which one is experiencing the larger acceleration? Well, it turns out wherever the radius is smaller, you have a larger acceleration. You've probably experienced this, right? You drive your car around a tight turn versus a shallow turn at the same speed. You can feel that there's more centripetal force required to get you to go around a tight turn, right? If you try to go around too tight, sometimes your wheels can't supply enough centripetal force and they start to squeal and you kind of slide out of the turn, all right? Now we have one more step to get this in terms of a force. That just looks like this. Since F equals ma, if we multiply both sides of this by m, you get m AC equals mv squared over r. And then you write this formula down. Since that is ma, we just say Fc centripetal force is equal to whatever mass I have times its velocity squared divided by its radius. Okay, and we're going to have one last thing here. Okay, since we're cranking out formulas, let's think about this. So let's say I have a circle and I have an object going around and around and around the circle, right? So here it is. Okay, it's got some radius r. And let's say that this object has a period, t. That's the time it takes to go once around, right? How do we find the velocity of the object? Well, we know that velocity is equal to the change in displacement divided by time. Really what we're talking about is just the magnitude of velocity, kind of like the speed. So what we could say then is we could say this is the speed of this object is going to be the distance it went. So in that case, the distance it went is equal to its circumference divided by the period, right? C over t. Now the question is, how do I find the circumference of a circle? Can I just do 2 pi r? 2 pi r over t is equal to the velocity. So let's take this formula and put this into it. Okay, so now we can talk about centripetal force in terms of the period and the radius rather than the velocity and the radius. It's often not directly obvious what the velocity is, but if I see an object spinning round and round, it's not too bad often to find what its period is. I just need a stopwatch, essentially. So let's start with this. Fc equals mv squared over r. And then let's put in, for velocity, this. So now we have m 2 pi r over t squared all over r. And that becomes this, m 4 pi squared r squared over t over r. Just move that up. That's okay to do. And that's going to cancel with one of those. We get this, m 4 pi squared m4 pi squared r over t squared. Sorry, forgot to square the t. T squared. There. Sorry about that. Good catch. m4 pi squared r all over t squared is another way to write Fc, centripetal force. So we'll write it all again. All our equivalencies. Okay, there. There we go. Done. So this is nice, right? But we spent a whole bunch of time learning all about omega. So how does omega fit into all of this? Well, we figured this out, right? This is angular frequency in radians per second. Okay, multiply that by the radius, and there's your velocity. So can we take that and put it into this formula? The answer, of course, is yes. Yes, we can. And then what do we get? We get m. And then we pull at the end, right? Divide that off. Okay. So one more way of talking about it, if you are given angular frequency rather than period. So as a final note, let's write it all out. Okay, and I think that's it.